All right, this is not the chapter where they talk about Caesar cipher because it would be appropriate. I mean, I know that y'all in Ken's class have already gotten past that point, but I thought yeah, here we go. So we're pretty close to that. So here's an example of a loop that's just stepping through a string, printing out each letter and their position. Right, so for index in range, len data, print both the index and the data at that element. Right, so here's our string, so that's index 0. The index is going to count from 0 up to, but not including the length of it. So it looks like the length of this is about 9. I've got that right, so it's position 0 through 8. And there we go. So we could also print out their ASCII values if we so chose. What are the ASCII values? Well, every letter that we see displayed on the screen has to have some kind of numeric value so it can be stored in memory, because everything in the computer is ultimately a number. So there's a thing called the Ascii Table, invented during the 60s, I believe. The first version of the Ascii Table didn't even have lowercase letters. Now it does have lowercase letters, but so an uppercase A is a 65, and an uppercase B is a 66, and so on. Well, we could find that out. We can make Python tell us the ASCII values of a string that we enter. Let's play with that idea. I believe we're on Lecture L. Define Lecture L. Instead of main and main 1 and main 2, thought it'd be fun to call it by its lecture name. And then down here we're going to have to just call Lecture L, right, to actually get it to run. So Lecture L, parentheses in parentheses, to invoke it. So it's going to be really annoying if every single time we run our program for debugging, it asks for a string. So why don't we just enter, hard code one? So string or data, they like the word data. So data equals, quote, hand shot first. Exclamation mark, end quote. Yeah, we're Star Wars fans, and we don't like that George Lucas edited that scene in the movie.
So, talking about the scene in the bar?
Yeah. Because in the 70s, Han blew Greedo away, and then he edited the movies to make it look like Greedo and Han fired at the same time, or that Greedo fired first to make Han not such a bad person.
He was a smuggler.
Yeah, I know.
To do?
I know. It was a stupid edit. So
if you really look at the beginning of him,
yeah,
shoot, that was his.
It was a dumb change, just like when Steven Spielberg re-edited E.T. and had them, use computers to white out all the guns the policemen were carrying and replace them with walkie-talkies because guns are scary. Yeah, people make stupid changes to movies. So, anyways, let's write something that'll step through this. Now, they show an index-based loop here to print out the numbers. We could do that, or we could just use our cool value-based loop, right? So for CH, and I'm just using CH to mean character. For CH in data, for every character in the string, for CH in data, colon, firstly, let's just print it out, and then we're going to make this a little bit more sophisticated. Print, parentheses, CH in parentheses. And so it's going to print out the letters H, A, N, and so on.
Question.
Yes, sir.
Does it matter how you okay, never mind. I just answered my own question. I was going to ask about the indentation, but
yes, it does matter. Yeah, the indentation matters because, yeah, you know why.
yeah.
And this is the end of our function, right? So end lecture L function. Just putting a little comment there. All right, and so it printed out hand shot first. Now we can get the ASCII value of each character using what's known as the ordinal function. How about AV for ASCII value? AV equals ORD parentheses CH in parentheses. So we're going to print out not only the character, but its ASCII value.
Is that what word is?
Yep. In this particular language, ORD returns ASCII value of the character. Now I'm going to modify this print statement to make it look a little bit more sophisticated because we might wind up even wanting to print the hexadecimal values. So, to prevent us from having to make more changes later after we've already made it complicated, I'm just going to replace it. Print, parentheses, quote, %s, meaning string, ASCII value, not ASCII. Need to douse the lights a little bit more. ASCII value equals %d. And then find out the hexadecimal version after it. So %x displays a number in hexadecimal, whereas %d displays it in decimal, base 10, right? And if you don't know what those mean, that's okay.
Like this, sir?
That's perfect. That's perfect. Thank you so much.
Well,
Is that %s?
Yeah, so x, let's make some little notes to this effect. %d equals base 10 number, decimal. %x equals base 16, hexadecimal. And if you don't know what those mean, that's okay. But you'll get to see the results. So after our closing parentheses and end quote, we need to put our %sign, and then an open parentheses and a closed parentheses and a closed parentheses to finish everything off. And inside the parentheses, we're going to put the character, CH, the ordinal value, the ASCII value, AV, and then we're just going to pass in the AV again to fill in the second place value, but it's being printed out in a different format, the hex value format. Yeah, because we got to fill in both the %d and the %x with that number. All right, and so we go. Here we go. HAN, uppercase H is a 72, a lowercase a is a 97, a lowercase n is 110, and we can confirm these values by going back to AsciiTable.com. Uppercase H is 72, lowercase a is a 97, lowercase n is 110, and then that space is a 32. And then there's another column for the hex values, right? So that 32 is a 20, and that uppercase H is a 48, and we will see that reflected in our output, right? 48, 61, 6E, 20, and so on. I'm going to play with this idea just a little bit more. I just want to write a for loop that's going to only print out the hexadecimal values. So to print out 48 followed by a space, 61 followed by a space, 6E followed by a space, 20, and so on. So we're going to write another loop that does the same thing, just present it a little bit differently. Same business though. For CH in data colon ASCII value equals ORD parentheses CH in parentheses. To get it to not go to the next line, we're going to use the end parameter on the print statement. So print parentheses quote %x space end quote %sign open parentheses, close parentheses, and inside here we're going to fill in the place value, the placeholder with AV. But we need to add the end parameter, so it won't go to the next line. I mean, and it'd be okay, right? It'll just print them all the numbers like that, but I want them to go across instead. So here, between the two closing parentheses, I need to put comma, ND equals double quote, double quote. That'll stop it from going to the next line. But just like you type in a whole line of data and then you hit the enter key, we have to go to the next line sometime. So underneath the for loop, lined up with for, no longer indented so much, we're just going to do that.
I have a question when you get a chance.
Sure. And so here is our string. Han shot first. We're going to make it even fancier, just because we can, and then I'll answer your question.
Okay.
Copy this loop. Paste it underneath. And instead of %x, we're going to change everything from here to here. So delete everything up to the comma and make this say %3s, end quote, or just %2s followed by a space, %2s, end quote, comma, ch, comma, end equals. You see the change we made to that? It now says %2, whoop, no, that's wrong. Why am I putting commas there? I needed that % sign there. You know, I'm going to paste this again because I've totally botched it. Replace that. Change %x to a %s, and instead of printing out the ASCII value, let's print out the regular value. I think we'll like the results better. We don't even need this ASCII value anymore because we're not printing it, so I'm going to delete that line. Then I'm going to run it, and I'll be open to questions. All right. No, that's not what I wanted, right? It's not spaced out enough, so let's add a second space after the %s. I want 2 spaces there so it'll be padded out nicely. See? Han shot first. All right. Yes, sir.
Up at the first for loop,
Uh-huh.
where it says CH, comma AB, comma AB.
Uh-huh.
Why is it not printing where you're referencing the 2 ABs? I would assume that they're the same value.
They are the same, but one is being printed in base 10 and one is being printed in base 16, so they look different. If we change them both to be %D, then they'd look the same.
So go back.
Right? I just changed the format. Because what if this second one was %.4f, right? It's the same value, 72, and then it's just being printed in a different format each time. First one is listed as %D, the second one is %4f, and so it's printing it with 4 floating point values.
Okay, go.
And if we go back and we change that to x again.
So let me make sure I understand something.
Mm-hmm.
All right. So when you use the percentage sign with a letter, you have to have, after your whatever you have in quotes, you have to have the percentage sign and then in parentheses what you're referencing. Like
exactly. And so this one goes into there, that one goes into there, and that one goes into there.
Okay, that's what I was missing.
Right.
I got that. All right.
So I'm going to change this back to %x now. And they're kind of ragged, but I could specify the width so that they would no longer bounce back and forth, right? I could say %, where's our print statement? %3s, give myself room for 3 characters there. And then %3d, give myself room for 3 characters there. And then 3x. So it'll occupy 3 spaces. There. Now they're all nicely lined up. The 3 is not necessary, but without it, you know, if it was only 2 characters long, it didn't pad it out with an extra space. And so it started looking jagged. So just as a comment, take a look at the ASCII table. The difference between an uppercase A and a lowercase a is just adding 32 to it. Now maybe you've used binary numbers enough to know that 32 is, you know, a power of 2, something like that. So if you ever need to convert from an uppercase F to a lowercase f, you can just add 32 to it. Of course, if you have a lowercase f and you add 32 to it, it's going to mess it up. The idea behind Caesar's cipher is, what if you passed in ABC, but you added 1 to each letter before you printed it out, right? And so instead of being a 65, 66, 67, it was a 66, 67, 68. Then it wouldn't print out ABC, it would print out BCD. Or what if you added 10 each time, right? You had the string ABC, which is supposed to be 656667, but we added 10 each time, so it was 757677. We come down here, and so when we gave it ABC to print, it would print out KLM. That's what's called Caesar's cipher, because it dates back to the Roman times, you know, and you didn't want your guy on horseback or your runner or whatever to get caught with a message that the bad guys, you know, your enemy team could understand. And so they'd come up with something like that. So we could play with that idea. What we're going to do. To go back from the ASCII value to the character value, you don't use ORD, you use CHR. So like if we did this, C1 is equal to the CHR of 65, which is a capital A, and C2 is equal to CHR of 66, and C3 equals CHR 67. If we print those out, it's going to be A, B, and C. We're going back from the ASCII value to a character at this point. So if we do print C1 plus C2 plus C3, it's going to print out ABC. And so it did. So maybe you see the applicability. What if we added 1 to each one of these, right? What if we had a shift value? I'm going to say shift is equal to 0 to begin with. But inside of each one of these parentheses, and I'm going to wind up copying and pasting it to save some time, 65 plus shift, not shirt. And then 66 plus shift. Like I said, copying and pasting would have been faster. 67 plus shift. Now since the shift value is 0, it's not going to change it. It's still going to print ABC. But what if the shift value is different? What if it was 10? So it added 10 to it each time. Then just like I said, it's going to start at 75, which is a K, so it's going to print KLM. There we go. So we can take our original string and print out new letters based on shifting them to, you know, adding 10 to them. Let's do something like that. For, it's going to be kind of similar to this, but then we're going to change it a little bit. For CH space IN space data, for every string in our data, get the ASCII value of it, AV equals ORD parentheses CH, but then add our shift to it. AV plus equals shift. And then turn it back into a character. CH equals CHR parentheses AV. Take that ASCII value and turn it back into a character. And then just print that guy out. So print, parentheses, CH, in parentheses. And there we go. So instead of hand shot first, we now have R, K, X, asterisk, and so on. Let's print it out in that nice format where it doesn't go to the next line, right? Let's print it out a little bit better. So I think we spaced everything over by 2 characters to get it to look nice. So plus, I'm going to rewind, sorry. So print, parentheses, quote, %s, space, space, end quote. You know what, it's just this very statement right here. Just copy that one inside the for ch and data loop up here. So those 2 statements. Copy those guys. No, just copy that one. Paste it there. And then back tabbed 1 from the for loop, we got to print out our carriage return, so it'll go back. And there we go. So shifted 10, it's that. Well, that's hard to see, but if we shift just by 1, it's easier to spot, right? H becomes I, and J becomes K, and so on. So I'm going to edit the shift value back to 1 and run it, and it's going to look a little bit better, right? So instead of hand shot first, H is A is B, N is O, space becomes an exclamation mark. You may wonder why, but if we look at the ASCII chart, that's true, because the one that follows the space is the exclamation mark. Now this is not a perfect Caesar cipher. And why do I say that? Because a Caesar cipher is supposed to kind of wrap around at a certain point. Because what if we did something dumb like make a shift value that's, you know, too large, like 25? We might not like the results at all. I'm going to change this probably back to 1 after I run this test. But see, it's starting to print out some gobbledygook. We got a whole bunch of spaces, which are unprintable characters and whatever. So what should it do? Once it gets to the end of the ASCII table, like, you know, no greater than Z or something, it should go back and start from here again, right? So if you have a Z and you add 2 to it, it's okay to print that sign out. But if you have a Z and add 3 to it, it better not go past that. Oh, well, I guess there's a couple more. There's one right there. But it better not go past that one. So if we had that curly brace and we added 2 to it, it needs to come back over to here. So we're going to modify our code just a little bit more so that if our number is greater than 126, we're going to subtract a value to get back to 32. Yeah, I wish my brain worked that well, but I can't figure that out in my head. So 126 minus 30. Whoops, what am I doing there? I meant to open up Google. I could have figured it out by the time I did this. 126 minus 32 is 94. So if our new ASCII value is greater than 126, I'm going to subtract 94 to get it to go back to the smaller number.
You subtract 94?
Yeah. Why? Because, and I know the book probably shows something different. Because if we are here, like, and then we add 1 to it, we don't want to get to a delete character. Instead, we want to get back to 32. So if we are here and we're past that, is it not 90?
I see what you're saying.
But yeah, it needs to go.
You're trying to get back to 32, not
right. And and you're right though. It's not 94. I think it's 95 because 127 needs to get back to 32, and you can do that by subtracting 95. So I'm glad you questioned me on that. So if the ASCII value is greater than 127 colon, let's subtract 25 from it. AV minus equals 95. Same business. What if our shift value was negative and we went lower than 32? right? What if we, because you can have negative shift values. And so what if we had the number 0, but we subtracted 20 from it? Well, that would take us down to 28, and it would print some weirdo character off the edge of the map here, right, wherever 28 is. Right? We don't want it to print a cancel or whatever.
Yeah.
So instead, we need to add 95 to it if it's less than 32.
It looks like 28 wasn't there. It just went to 30.
I'm so sorry, pardon me. I'm deaf. Please repeat.
Oh, I'm saying, on there it looks like 27 just went straight to 30 and never hit 28.
Yeah, let's take a look at that. Yeah. Where?
There is no 28.
Well, that's weird. I never noticed that before, and I've been looking at this chart a long time. What is ASCII value for 28? Mm-hmm.
Maybe that's just a bad table.
Yeah, I think the table's missing something.
Yeah, 28's on that.
File separator and group separator. Okay, just some things that they didn't think we needed to know about. All right, so back to our code. If our number is less than 32, we're going to add 95 to it. So over here, if AV is less than 32, colon, AV plus equals 95. I put a semicolon there, and that's wrong. I'm sorry, I slipped into Java or C++ or something there. It wouldn't have broken the code, but we don't end our data, our lines in semicolons. So if you type that, even though it wouldn't crash your code, go ahead and remove that. And if we wanted to add some comments, what was going on here? Get ASCII value. Oh, I made one more mistake, and does anybody see what I did wrong? It's okay if you don't, but
Will
maybe.
we say elif or?
Yeah, we could do elif there. That'd be cool.
But if it's okay.
Either way would work.
Mm-hmm.
Okay.
But you know, if it's greater than 127, it shouldn't be less than 32. So elif is cool. But at what point should I be adding the shift to it? I should do it before those if statements. So I did these in the wrong order. So if you've typed this code in, delete that line, AV plus equals shift, and paste it above the if.
Could you do that in one if statement? If AV is greater than 127 or less than 32?
You could probably come up.
Because of the plus and the minus.
You could probably come up with some way of doing it, but yeah, since we have two different outcomes, I wouldn't try to. Yeah, the question was, could we do this in a single if statement? And I bet if you were cleverer than I, you could find a way of doing it. But I would just do it like that because we have two different outcomes being triggered by the results. If they were the same result, subtracting, 95 from it both times, absolutely. So we're getting the ASCII value, we're shifting it, I'm adding some comments. And then if it's too large, shift back, and then if too small, shift forward. And then turn back into a character, right? And then, of course, print it out. Don't really need to add that comment, but we commented just about every other line, so why not? It almost makes things too cluttered if you have too many comments, though, so I'm going to get rid of that one. All right, and so that was a shift value of 1. If we made it a shift value of -1, it would shift everything back, right? H would become whatever's before H. G. B would become A. A would become something else. There we go. Here's what it looks like shifted back by 1. T's become S's, H's become G's, and so on. So that's not a bad little code. I mean, of course, cryptography, and the NSA, would be able to crack that like in, about 0.1 nanoseconds, right? It wouldn't be any challenge at all. But just for displaying our information on the screen, it's okay. Now, one more coding mechanism that people used to use so that you'd have something that you could display on screen but it would be unreadable is known as ROT13. And ROT13 is where you just add 13 to it, and if it goes back around, if it comes back around, anyways, because then you could subtract 13. And the idea is that the alphabet is 26 characters long, and so you're just jumping from like the end of it into the middle or vice versa. But now that I'm thinking about it, I don't want to do that. And the reason why, I'm not going to even talk about it. Forget ROT13. You want to know about it? Google it up. ROT13. It's a simple letter substitution cipher, because that's what this really is. These are cipher. Where an A becomes N. You shift it by 13. A B becomes O. And so on. But you also have to figure out how to shift the punctuation, and you have to know how to fix the lowercase versus uppercase. So maybe it's just the shifting of a 13. Maybe it's just hard coding it to shifting 13 each way. All right. Why not? I'm going to change the shift to 13 just to see what it would look like if I printed it out in ROT13. There we go. R becomes something nasty looking. I wonder what that character really is. I'm not digging that. I guess I'm going to add 13 in my head to lowercase r to find out what that is, because I'm not liking the way that looks. Lowercase r plus 13. 1, 2, 3. Come on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is it possible that it equals 127? I thought. Yeah, let's make it greater than 126. And it probably still should have been 94 then, like I originally calculated. I don't know what I did wrong there. But if it's greater than 126, subtract 94. If it's less than 32, add 94. Well, I'm glad we did that little exercise after all. And now it doesn't have that, that alien-looking character in it. So that's displayed in ROT13. And if we took the spaces out, it'd look completely. Just for funsies, I'm going to take those spaces out momentarily. I'll put them back. But there's the same sentence. Han shot first, displayed with every character shifted 13. So if you wanted to, you could write a program that would ask the user for a string, and it asks the user for a shift value, and then it would shift it, right? And then if you took that string that it gave as output, let's do that, right? This is my output here. Don't make this change, because the code's already pretty good, but if I took that string, I made that my string before I started doing all this shift business. I don't know, sounds like, anyway. And then I shifted it. Oh, well, that double quote there is not going to work. And then I shifted that by -13. I would get back to my original data. Or not. I don't know what I did wrong there.
Is it because you fixed all the other stuff? Where you took it from 95 to 94 and from 127 to 126?
I kind of thought that was okay. Well, I'm going to get rid of that. Oh. It's because this should have been called data, right? That was the name of our data, not S. Please be the fix. I don't want to waste any more time. Right, and so it went from that one string back to being Han shot first. because we took the data that we outputted and we entered a negative value as a shift, and so we decrypted it. That's not the correct term. We deciphered it. Encryption is more complicated than a cipher. A cipher is just where you substitute one letter for another. Decryption goes way beyond that to make it, encryption goes way beyond that to make it more difficult. All right, I'm going to get rid of that. And my final change is just going to be shifting it by -1 just for funsies and leave it alone after that. Ooh, and I want to add those spaces back. I made too many changes. There. And I'm going to pause it, make sure everybody's happy with how their program's working. So now it's going backwards. O becomes N, F becomes E, S becomes R, and so on. I believe that the PowerPoint also has a Caesar cipher going on in it. It'll be interesting to see how theirs differs from ours. This is talking about slicing, or substrings, just like we did before. Name 0:1. How many characters is that going to pull out? Just one. So it prints out an M. You could see that from down here. But how did we figure that out fast? We take this second number, subtract the first one, and that's how many long it's going to be. So here, 2:6, we know that it's going to start at 2, and it's going to be 4 long, because 6 minus 2 is 4. Drill to extract file. Well, isn't that a strange way to put it? And here we're using the in keyword, IN keyword, which Dev asked about last time. How do you check to see if something is in something else? If something is in something else. So here we have a list of words, and we want to see if any of them have .txt in them. Let's do that. Something similar. Maybe not the exact same answer. You wouldn't want to copy them too much. So we're going to print out only the vowels in that sentence. Hans shot first. So here's what we're going to do. For CH in data, colon, and if that character is in a list of vowels, if CH space IN space quote AEIOU lowercase AEIOU, and I'm going to leave out Y because sometimes it is and sometimes it isn't. So if CH is in AEIOU, we're going to print it out. Print CH. Otherwise, we're not. So let's print CH, comma, END equals quote, quote, just so it won't go to the next line. But after our for loop, we're going to need to print a blank, character turn. So I'm going to back tab, make sure it's lined up with for, and print out, get to go to the next line. So now I should just print out all the vowels in Hans shot first. Not very many of them. 3 to my recollection. Right, A, O, and I. What if we wanted to print out the consonants? We would say if not CH in AEIOU. Now it's going to print out everything that's not a vowel. There. Hans for a fur. So what have we learned so far? ORD, ORD gets ASCII value. CHR gets a character from an ASCII value. %S is for printing strings and letters. %D prints a number in base 10, just like normal. I'm not going to even add that base 10. %X prints a number in hex, short for hexadecimal. And for CH in data, steps through every letter in a string, except I'm not going to make it letter because you can have digits and spaces and stuff like that, so steps through every character in a string. You don't have to call it CH though, right? You know, if we want, don't make this change, this is dumb, but I can make this Fred, right? For Fred in data, if not Fred in AEIOU, print Fred. It's going to work just the same. Variable names, you know, mean something to the humans, but they don't matter to the computer. Now I'm going to undo those 3 changes. Let's set up some new data now. Although I should let you type in my notes. I know I type faster than y'all. Something like this. Data equals, and then just type in, you know, whatever. Just wail on it. Just make sure you put an end quote at the end, right? Please don't bother typing in the exact same thing that I did. You saw what I did. Say we only wanted to print out the digits in that string and we wanted to skip everything else. We would use isDigit for ch in data colon if ch dot, oh, let me make sure I get this exactly right. I don't want to type in something, I have to fix it. Python isDigit. Yeah, okay. So if ch dot isDigit, parentheses in parentheses colon, let's print it out. Print parentheses ch comma end equals quote quote, and then after our for loop, just like the other times, back tab 2 times, and then print, you know, a character term. So it's just going to print out all the digits.
I should probably already know this, but what is just the open close parentheses mean again?
Like here?
Yes, sir. And like
because every function has to have parentheses when you call it, or else it doesn't know that it's a function. And so even if we're not passing any data into print, we've got to have the parentheses there. And so print parentheses in parentheses just tells it, okay, print, and since print always goes to the next line no matter what you have in here, it just makes it go to the next line. If I didn't have that, then every time we use this END parameter, then after it was done, it wouldn't go to the next line. Right? It'd be like you type forever without ever hitting enter. Is that making sense? Because we can define our own function.
So having print open close parentheses just
it's like it's just printing out a character term. It's printing out nothing but then going to the next line.
So like in typing, it's just hitting enter and
yep.
going to the next.
Exactly.
So
yep.
it's showing your user that you're done with whatever.
Right. Because if I didn't have that and then I printed something else, then it's going to print wow at the end of that. But I don't want it to print wow at the end of it. I want wow to start on the next line. So this makes it start on the next line. Makes it just like hitting enter on the keyboard. Yep. That makes sense, gang?
Yes, sir. Thank you.
And now just copy this for loop right here, those 4 statements, and let's print out the letters involved rather than the digits. So we're not going to use isDigit, we're going to use isAlpha. And you can guess what isAlpha means. Alphabet character. And make sure you tab everything right. But change isDigit to isAlpha. And there we go. It printed out only the digits, and then it printed out only the letters. There's even more versions. There's isUpper to check to see if it's an uppercase letter. or is lower, or is alnum, which means is it a letter or a number? So it wouldn't allow punctuation. I'm going to keep going, but then I'll pause and we can come back to this and help correct typos if need be. So data encryption, ciphers, Caesar cipher and block cipher. Now, since I haven't read this since last semester, I've kind of forgotten what a block cipher is. Let's go look. Caesar cipher replaces every character with a character some distance away. And we've talked about that now. A becomes D, B becomes E, C becomes F, and so on. Here's their code for it. Very similar to ours, though, right? ORDCH gets stored in ORD value, except we call that AV. And then we called our shift rather than distance. And instead of checking to see if it was greater than 126, they checked to see the ordinal value of Z. Works. Instead of subtracting 94 from it, they calculate that 94 by another mechanism. Yeah, whatever. And then they add that to it. The only difference is that they create an entire string before they print it out. So their print statement was not in the for loop, it was after it. If we felt like doing that, we could. Maybe we'll modify our code to do that, I don't know. Yeah, let's do that. We're going to have to copy and paste our Caesar cipher code, but we're going to take out the print statement. So just copy all that. Paste it below it. Comment out the print statement. We don't need that anymore. And instead, we need something to hold our result. What did they call that string? Code. Okay, fine. So above my for loop, and I know I mess people up when I go back and edit earlier parts of the code, sorry. Code is equal to an empty string. And then each time we figure out a new character, remember this, I'm editing the copy of the for loop, not the original one. Each time we figure out a new character, we're going to add that to our code. Code plus equals the letter we just figured out. And then we could print that character out. So underneath our for loop, print that character out instead of printing out a blank line. Now this matches almost exactly what their code does, except with different variable names and different ways of calculating 126 and 94.
So we take, you commented out that you didn't delete it, did you?
Yeah.
The print.
Right.
Thing? Okay.
I don't, am I convinced that it actually printed it out? Oh, why did I print out CH? What did we actually store our resulting code in? Variable named code. So I'm going to add a comment up here to the top explaining what we're doing there. And there's our result, right? That is our enciphered text. So I'm going to add a comment above that code equals empty quote. Build a string with Caesar's cipher and then print the string out. This is what the book does in a slightly different fashion. So they show two different functions, or two different chunks of code. In fact, two entirely different programs. Their first program is called encrypt. Their second program is called decrypt. You just do the same thing, right, but with a positive or negative shift value. So I think ours is more awesome than theirs. So a block cipher uses plain text to compute two or more encrypted characters. Uses an invertible matrix. Well, that's a fancy way of talking. What block cipher means is that you can use one set of characters to encipher another one. That may not sound real clear yet, but if we're looking at our Ascii table, what if instead of adding 1 each time, we added 1 to the first one, 2 to the second, and 3 to the third, and added 4 to the fourth one? It'd be more unpredictable, right? It'd still take the NSA, 0.1 nanoseconds to crack it. But if you gave that to somebody and they needed to, undo it by hand, and all they knew was Caesar's cipher, it would blow their mind, right? Because the first character you shifted by 1, but the second character you shifted by 2, the third one you shifted by 3, and so on. Well, a block cipher is, instead of using a sequence like that, 1, 2, and 3, what if instead you used a series of letters like B, E, A, D? Well, for the first character you might shift 1 because that's the difference between A and B. The second character you might shift 5 because the difference between A and E is 5. The third character you might not shift at all because the difference between A and A, And then the fourth one you would shift 3. So if you encrypted using a block cipher your sentence, your shift values would be 1, 5, 0, 3. And then you would keep repeating that pattern over and over. And then when you wanted to decrypt it, you would shift by the negative of those values. A B is a -1, -5, -0, yeah, right, and -4. So that's a block cipher, and we're not going to write that code. I think they have it here. I'm going to leave that alone.
It's in the notes. It's in the
Oh,
chat.
how sweet, they didn't give it to us. Maybe it's in the book, but not the PowerPoint. All right, so strings and number systems. Arithmetic operations use the decimal number system. We've got 10 fingers. If we'd grown up with 12 fingers, we wouldn't use base 10, we'd use base 12. Binary is a base 2, meaning there's only 2 digits, 2 fingers, 0 and 1. And then there are other number systems. There's octal, which has only 8 digits, 0 through 7, and then there's hex, which has 16 digits. How do you get 16 digits? Well, you use some letters as well. A, B, C, D, E, and F represent the numbers 10, 11, 12, 13, 14, 15. So you could have a number in binary notation, in octal notation, in decimal notation, and in hexadecimal notation. And they better show us how to do it. To represent digits with values larger than 9, you can use a base 16. I'm not going to teach y'all how to convert by hand. This is not a fundamentals of programming course. If you want to learn how these math values actually work, because that's a whole lecture unto itself, I can link you to a YouTube video. If you want to learn more about this and the book isn't clear enough, text me a message and in fact, I'll just find it and I'll post it in our announcements. But you know that we have powers of 10, right? You have the ones place and the tens place and the hundreds place and the thousands place. When you're using binary, you have powers of 2. So you have a ones place and a twos place and a fours place and an 8 and a 16 and a 32 and a 64. So if you have 1, 1, 0, 0, 1, 1, 1, that means you do have a 64, you do have a 32, but you don't have any 16s, you don't have any 8s, but you do have a 4 and a 2 and a 1. And so you add those up and that gives you your answer. So converting from binary to decimal. And they give you a formula for doing that. We could type it in. You could look at the code yourself and type it in. I believe that one of the MindTap problems has you converting from decimal to binary or vice versa. You can probably find the code to do that in here. If you get totally stuck on it, you know, we could talk about it next time. And how to convert numbers from decimal to binary. You just keep dividing by 2 each time, and then you record the remainder. Now, I don't want y'all to type this in as notes, so I'm going to do it in Notepad. But if you have the number 93 and you want to convert that to binary, you just keep dividing it by 2 and writing the remainder. So 93 divided by 2 is like 46 with a remainder of 1. 46 divided by 2 is 23 with a remainder of 0. 23 divided by 2 is what? 11 with a remainder of 1. 11 divided by 2 is what?
5 remainder 1.
Yeah, 5 remainder 1. 5 divided by 2 is 2 remainder 1. 2 divided by 2 is 1 remainder 0. And 1 divided by 2 is 0 with a remainder of 1. And now we're done. And then to print it out, it's 101, 1101. So that's the answer, 101, 1101. And then if we were to add them up, you know, there's a 1, there's no 2's, there's a 4, there's an 8, there's a 16, there's no 32's, but there's a 64. So it's a 64 plus, I'm just going to go backwards. 1 plus 4 plus 8 plus 16 plus 64. And I can't add that up into my head, but Google's awfully smart. They can. Should equal our original number, 93. So that's how you convert from decimal to binary. And this code would be a lot easier if they properly tabbed it. When you're looking at their code, it's almost a puzzle to figure out, but it's correct in the book. You have to tab everything yourself. So if you're going to type this in, don't be fooled by the fact that they don't show tab correctly. Just realize that the PowerPoints, whoever shipped them out, didn't tab them correctly, and I keep forgetting to correct them. Now here I'm wondering how they reversed it. Right, because I told you that you had to write the numbers, you know, in reverse, 1011, 1012. Looking at their algorithm for figuring out, you know, how did they reverse it? Oh, they just add the remainder in front of it. What do I mean by that? You know, I'm always thinking like this. A equals A plus 1, right? And so each time you got a remainder, you tack it on to the end. Instead, they did A is equal to 1 plus A, right? And so they put it at the beginning of it, and that's how they built the reverse string. Clever. Don't know why I didn't think of that. We're going to have to wrap up pretty soon. You can do a shortcut and not use these algorithms. You can instead convert just like I showed you with that %D. Excuse me, that %X. And there's probably another one to print out binary. I bet it might be %B. Let's find out. Let's come back here and print, parentheses, quote, %X, that's the hexadecimal version, end quote, comma, 93, in parentheses. Nope, not comma, I forgot, this is Python, so put a % instead. Notice I left off the second pair of parentheses. If you're doing it for only one value, you can leave off the parentheses. But to be just like I was before, to be consistent, I'm going to do that. Put the 2 parentheses around it. Let's see if we can print out binary the same way with %B. I don't know if this will work. It'd be kind of cool if it did. Nope. Alrighty. Got to be a way. Python format output binary. Oh. Different way. This is old school. This is Python 2 way, using those percent signs. Here's Python 3's way. Print, parentheses, quote, open curly brace. Let me make sure I get it exactly right, and this will be the last thing we talk about today. Yeah. 0:x, end curly brace, end quote, dot format, parentheses 93, end parentheses, end parentheses. Let's make sure that works, and then we'll do the binary version of it too. So yeah, then copy that. Let's do it 3 times in a row. We're going to print :D, :X, and :B, meaning base 10, base 16 or hex, and base 2 binary. And there we go. Right. 93, no surprise. 93 in base 10 is 93. 93 in hexadecimal is 5D. 93 in binary is, when we've already calculated that out, and that looks kind of right. So you don't have to use a fancy algorithm if you let it do that, right? So say you had a number, num equals 93, and you wanted to convert it to binary. You could do it like this. Binary equals, quote, curly brace, 0:B, end curly brace, end quote, dot format, parentheses num, end parentheses. And then you can print that out if you wanted to. We've already printed it out, but you don't got it. We don't need to do it again, in my opinion. If you wanted to get a string in hex, same business. The hex string is equal to all of this same stuff, except change that B to an X. And I, by the way, don't use the word hex because that's apparently a keyword. How about hexa equals, just paste all that and change that B to an X. All right, I'm going to give us a break on the daily homework assignments so that we can catch up. So I'm not going to assign any extra homework this time, but I would start working on the finish off Chapter 3, absolutely, if you haven't done the Chapter 3 mind tap. Get that done over the weekend and then start chewing on Chapter 4. Get far enough into Chapter 4 so you can ask me, you know, say, hey, I can't do this one, and we'll do one of them in class. That's always cool. So print parentheses num, comma, binary, comma, hexa, just so we see our results. There they are, right, 93, and then the binary and the hex version. Now, I never really remember to show you all this format, and the book uses the Python 2 syntax. They keep using these percent signs for your placeholders rather than these curly braces. So it's no wonder I forget to show you dot format, because it's not what the book shows. But this is the more modern way of doing it. This is a Python 3 way of doing it. And it looks almost exactly the way you would see it in other languages such as C#. So it's not bad for you to see it at all.